My name is Chikaiman Mbagu, and this is my lab on projectile motion. So in terms of the introduction, the purpose of this lab is to observe an object that has both a drag force and a gravitational force. The observed motion will then be compared to two models on the accounts for both gravity and drag force, and one that accounts for only gravity. For this experiment, the system is a ball, the surroundings are everything else, and for the observation, we will use tracker, and the computation, we will use GlowScript. So in terms of the equations / foundational principles that we need to understand the motion of the ball, we will be looking at net force and its relation to the change in momentum. Also, the velocity update formula right next to it that could be derived from that equation. As you can see, the net force over mass equals acceleration, which also relates to the change in momentum. Then also the position update formula under small time frames in combination, and that is in conjunction with the average velocity that can be derived from VF plus VI over 2, and the gravitational force that relates to the force acting on the ball, and also the drag equation, which is the force that is acting against the motion of the object. So in terms of the data on this graph, y1 represents the observed motion from the tracker, y2 represents the simulated motion with only gravity included, and y3 represents the simulated motion with gravity and drag force included. From these results, our calculations are much more accurate when we include drag force, as there are clearly other forces besides just gravity affecting the ball during its parabolic motion. So in those simulated versions with only gravity, or just the observed, or like the simulated motion with gravity and drag force, if we compare the two, taking into account drag force allows for a more realistic model of the motion. Here is just a screenshot of my lab mate, and we used a ball in this experiment, and the ball's mass was 51.38 milligrams. And then we calculated the initial velocity as the vector of 1.62, 2.61. And our initial position was just set at the origin. So the initial position, we set that at the origin to get a basis for how the coordinates change over the video. And then you could also see the parabolic motion that is modeled from the tracker and the data points that we use to begin our code. So here's our code showing simulated motion, but just taking into account gravity. This is similar to the code that we did from lab 1, just with a different initial velocity of 1.62, 2.61. And it's only in the X and Y component because of the way we recorded the video. And the position vector is 0, 0. We set the ball's mass, gravity is 9.8, and then we just set it in a time loop. And then here with gravity and drag, we did set the drag constant in this scenario to be negative 9.6. And the ball's position was negative 0.03 to be more accurate. And the ball's mass stayed the same. And that just added a layer of nuance to our model to ensure that it was more realistic to the ball's actual motion. And then in terms of the comparison of gravity only to the observed model, you can see a huge gap because in reality, the ball has a plethora of other forces acting on it, like air resistance. But in this case, the model is way more accurate to the observed motion when we're taking into account drag, if we look at the two compared. And then here are the three graphs together to really show the difference in comparison in terms of how much it relates to the observed motion of the ball. Some possible errors could have been air conditioning and other wind forces that might have acted on the ball. In the ball's shape, because it was had a rough exterior, it could have affected the way the ball moved, and it might not have been in a perfect parabola. And position tracking, placing the center of mass of the ball we couldn't zoom in all the way, so it might not have been the exact center. The model does not predict the terminal velocity because the velocity decreases linearly over time, indicating constant acceleration due to gravity without any limiting force. The gravity and drag model suggests the presence of a terminal velocity. The curve is slightly nonlinear, implying that drag opposes motion and reduces acceleration over time, eventually leading to a velocity that stops changing significantly. In the gravity-only case, the time to hit the ground would be the same as the time taken to reach the peak in terms of if the ball was thrown straight up, because the motion is symmetric. In the gravity and drag case, the ball would take more time to return to the ground. The drag force reduces the upward velocity faster than gravity alone, leading to a slower descent compared to the ascent. Thank you for listening.